Hey everyone, welcome to Computer Vision lecture number 22. It's already Thanksgiving, close to Thanksgiving break. That'll be next week. It's cold outside, which is nice. It's always nice to have some actual cold weather in the winter. How's my audio and video? Is everything sounding okay, guys?
Yes, Professor.
All right, great. We'll keep the video on. If there's an issue, we will turn it off. Okay, so let's go ahead and do some announcements, then we'll kind of get into the main topic of today's lecture. So first, just an announcement about grading. You may already be aware of it, but there's an option to switch your grading to a pass-fail. So I'll let Arvind give a little bit more detail. So I'll hand it over to you, Arvind.
Hello, everyone. So the graduate school is actually requesting the students for a pass or unsatisfactory grading if they require for this fall semester, like what we did for the earlier semester. But this semester it is a bit different. You have to submit a petition, uh, going to the academic petition in my UNCC. So the deadline is December 14th. So please make sure to submit a petition if at all you require a pass or unsatisfactory grading instead of the normal conventional ABC grades. And there is a however there is a one thing which is it might not be applicable for core courses which requires grade of B or better. So just make sure you check these things and submit it before December 14th. If you have any other questions, please contact the graduate school. Thank you.
Great, thank you, Arvind. So yeah, so the university has extended this pass-fail option to you. I think, and I guess I didn't know this, but that's what they did. So last semester, did all classes become pass-fail, or was it optional like it is this semester?
It was optional, Professor.
Okay.
Like the students can actually select whether they want a P or A or B or C.
Okay, interesting. And I apologize, I'm not aware of how the GPA stuff works. So Arvind and Rohan, do you know how that, so if a student receives a pass, is that a 4.0 or does it factor into the GPA differently?
I think it won't count to the GPA, I guess.
Okay, so it's excluded from the GPA. Okay, so the students who may be interested in this, right, or the students who may believe that they may receive a B or a C, I think, would be the ones who'd be interested. Is that the main reason students would be interested?
Yeah.
Yep.
Yes, exactly. And but this thing is only for the graduates, not for the undergrads in this course. And
Right,
also
right.
and also for the grad students who are doing computer vision as a core course,
Mhm.
this might be an exception. So just make sure when you're applying this.
Okay, great. And the university is they're trying to be helpful here as you're thinking about your GPA. So we've received a couple emails about it. Hernan has asked if there's been an email about it. I know that the instructors and TAs, I believe, have received an email. Do you guys know if the general student body has received an email about this?
I'm not sure, but I just received. Oh yeah.
So Pooja says no, Monica says yes, Abhijit says yes. It might depend on who you are. It might not be sent to everyone. Maybe it's only sent to the eligible folks. So it appears some students have received it though. So
I
maybe
can I
it's
can
only,
put I can put a screenshot of that on Canvas.
that'd be great. Yeah, thank you so much, Arvin. Great. Okay, excellent. Yeah, no, not an option for undergrad, right? Okay, great. All right, any other announcements, Arvind or Rohan?
Nothing, Professor.
No,
All
Professor.
right, great. Okay, all right, so let's pull up our schedule here. So we are getting close to Thanksgiving break. Um, your, you only have 2 quizzes left and 2 programming challenges. Again, these shouldn't be as bad as the last programming challenge. The deep learning one is a bit difficult, but it's not as bad as the neural network from scratch challenge. And then the final programming challenge it's meant to be a little bit more fun. It's not actually a machine learning challenge. There's no leaderboard. It's a little bit more creative. In the final challenge, you get to make your own 3D reconstruction. And we've seen some really cool submissions on this challenge, but this one's meant to be a little bit more fun. So it shouldn't. Where we've tried to make the course set up in a way that really now is the time that you can really focus on your projects. Okay, so we've made it here, and we're supposed to talk about just GANs today. And I was looking at my lecture notes yesterday, trying to figure out what to do exactly. Because the challenge is this. So this stuff always takes longer to get through than you think. I scheduled a whole extra lecture here, and we've already used it. And we're about halfway through the Deep Learning in Depth Part 2. And I was looking at these topics, and I thought about just leaving them out and going right to GANs. But a number of these topics are really, really important to your understanding of deep learning. So I think what we'll do today is we'll pick up on lecture 2. We'll finish up deep learning in depth part 2. And then we'll start GANs. And we may pick up and finish GANs here, or I might do something like just record part of a lecture for this. We'll see. GANs are really, really, really cool, but I'm not really going to quiz you on GANs. They're kind of more fun. And I don't believe we have any, maybe one group doing GANs for the group projects, but these are more just interesting and fun, but I do want to talk about them for sure. So the point I'm trying to make is I won't leave out part of this lecture because the details of deep learning in depth are important when you're training these models. So I think that this lecture is more relevant to you guys as students. And we'll either do half of this lecture now, and maybe I'll post the other half, or maybe it'll just be extra reading for you guys to look over. We'll see. But I'm going to hop into the remainder of the deep learning in depth lecture part 2 now. So let's see, my screen should update. Okay. So yeah, in the interest of moving quickly, because we have a lot of material to cover, and I want to make sure that we get a lot of these important deep learning topics discussed. Let's go ahead and pick up here. And just to remind you, in deep learning part 2, we talked about Jan LeCun and his work in the 1990s. And we recognize that, many of the features of a modern deep learning neural network were really developed in the 1990s. So things like convolutional layers, pooling or subsampling, a lot of this stuff existed back in the 1990s. So we asked ourselves the question, why did it take 20 more years for this really to become popular? And a big piece of this, a part of it is compute power for sure. But part of the problem is actually data as well. So we brought up Fei Li, and she's this awesome researcher who she created the world's largest labeled data set in the mid-2000s called ImageNet. Even though it wasn't a very popular idea at the time, it's become a wildly popular idea now. We looked at the ImageNet data set. It's got around 1 million images labeled. We watched them kind of fly by like this. I'm looking at the feed that you guys are seeing, and it's updating very slowly, but the feed that I'm seeing actually updates 30 FPS. So you may want to go watch that video later if you're interested in seeing all the details of ImageNet. So we talked about this paper called AlexNet, and this is your required reading for this course. So you should have had a look at this paper. If you're only going to read one paper in deep learning, this is probably it. This is the first important, I'd say, or maybe the most important modern deep learning paper published in 2012. So we talked about the AlexNet architecture. It's a deep neural network. We talked about it being divided into two parts. Why was AlexNet divided into 2 parts? What was the reason for this? Yeah, 2 GPUs, right? So Alex Krasinski couldn't really use one GPU because there wasn't enough RAM, right? So we had to split it apart like this. And then we started walking through AlexNet. We started walking through AlexNet to see the outputs. And we looked at the raw output here, which is an 1,000-dimensional vector. And we remembered, oh, we have to put this through a softmax layer. So you put this through softmax, and you get something like this. And then if you take the argmax, which gives you the index with the maximum value, that gives us the class, which is a golf ball prediction for that image. Now, the next thing I really would like to do is to walk through AlexNet in a little bit more detail. So here is the architecture. Oops, sorry. Here we go. Cool. So here's the architecture, like we mentioned last time a little bit. So it's got 5 convolutional layers, followed by 3 fully connected layers, 3 linear fully connected layers. It's got this average pooling thing in the middle, which helps us deal with images of different sizes on our input. But that's the network. And what I want to start to show you is this. So this, I think, is really, really interesting. Do I have the figure from the paper? I do not. That's okay. Maybe I'll pull that up real quick. But here's what I'd like to show you first. So what I've done here is I've taken this first convolutional layer. So the first convolutional layer of AlexNet is it's a layer with 64 filters. It has a kernel size of 11 by 11. We're taking a stride of 4, which means the kernels walk across the image in steps of 4. That's not too important. But what I really want to visualize together is I want to look at the weights. So, each of these kernels that's used to process the image in AlexNet, it's an 11 by 11 grid, right? That's dot product with the image. And we can actually visualize the weights because these little kernels are 11 by 11 by 3, right? So we can visualize them as RGB images. So let's do that. Here they are. Here's some of them. So these are the weights that AlexNet learns all by itself from data. Here they are. There's 64 of them. Here they all are. And what do you notice, right, when you look at these, right? What has the first layer of AlexNet? What does it learn to do all by itself? What do you see here? And remember that these kernels are cross-correlated. They're used to process the image, right? So if you took a kernel like this one here, right, and you slid it across, can you see my mouse? Let's see. Oh, now you can. It's kind of small. So if you took a kernel like this, right? So I want you to let's remember. Let's think back for a minute, way back to lecture number like 3 or something, right? Do you remember we talked about things like the Sobel edge detector, for example, right? And remember that that was kind of structured to find like vertical edges, right? And it kind of looked like a vertical edge, right? So if you remember, the Sobel filter had like a pattern of 121, 0, 0, 1, 2, 1. So it had like 2 vertical lines in it, the Sobel filter. And that little pattern helped the Sobel filter find vertical edges. So if you think about doing a dot product, well, let's take, who do we want to take? Let's take this, maybe, well, who's a good one? Maybe this one right here. Think about this pattern for a second, right? If you took this pattern and did the dot product of this pattern with an image, right? What types of image patches will give a high value for this dot product? Does that make sense? So what types of images, right? Just taking this little patch right here. Hopefully you can see my mouse. Yeah, right down here. Um, what do you think? What type of image pattern would really activate this filter? I think you guys are kind of sleepy today. That or I've totally lost you. An Oreo. All right, so I appreciate Hernan's guess, and maybe it's black and white, right? But what I really want you to look at is this vertical structure, right? So the idea here, and hopefully this will become more clear as we look at some more examples, the idea is that if part of an image has a similar vertical structure, if it has a vertical edge like this, going from white to black or black to white, this will trigger or match this filter very well. And that will cause this neuron to fire more, basically. This would detect like a diagonal edge. If there's a diagonal edge in an image, this will trigger this neuron. I hope that makes sense. Really, these are kind of like pattern matchers, right? The neural network has learned to look for all of these patterns. It's learned to look for all of these patterns. And a lot of them are edges. Some of them are kind of like texture patterns. So like here, this is kind of looking for a texture. Sometimes the network will learn what's called like a blob, right? So this network has kind of learned to look for a blob, for example, or this neuron. Here's kind of a magenta and green edge. But these are really, you can think about this as the patterns that AlexNet has learned to look for in the data all by itself without us ever telling it, what to look for. Let me show you one more thing. So if I pull in the AlexNet paper, I think that they do a similar figure, I believe. So here's the AlexNet paper, which was, like I said, part of your reading. So you should have had a look at this. And let's have a look here. I think, oh yeah, here we go. This is cool, yep. So here's the same thing in the AlexNet paper. I visualized it for you in the notebook, right? But here it is from the author of the paper himself. And this is actually, I think, really fascinating. So see, there's this top group of filters that were learned by the network. And there's this bottom group. And notice that the bottom group is mostly color, and the top group is mostly black and white. Does anyone know why there's 2 groups in the first place? Why they've broken this apart into 2 groups in the paper? Yeah, 2 GPUs, right? And all by them, this is crazy. So all by themselves, right? these GPUs have naturally specialized. So they somehow, in the course of doing backpropagation, the neural network decided that GPU 1 is going to do black and white, and GPU 2 is going to do color, right? And not perfectly. There's one color on GPU 1, but isn't that wild? So this is apparently fairly repeatable. If you break apart your network like this across 2 GPUs, which we don't really do anymore, sometimes, but generally not like this, one of them will learn color patterns and one will learn black and white patterns, which I think is the craziest thing. Like, that blows my mind. So these are the results from the AlexNet paper, and I hope that makes sense. And what I really want to emphasize, like, if you're going to take one thing away from this, what I'd really like you to take is this. So, back in the 50s and 60s, the Sobel filter was developed, for example, and when we learned about the Sobel filter, these are the kernel values, right? You've got 1, 2, 1, 0, 0, 0. Hopefully this rings a bell back from the first module that we covered. What we're doing in deep learning is we're just learning these filters. So we're learning multiple layers, and we'll get into why the layers matter shortly, but we're learning optimal values for these filters instead of guessing, right? So, Erwin Sobel, when he developed the Sobel edge detector, he kind of took an educated guess. He said, okay, this is probably a good filter, but he didn't know, right? So here we're using data to learn an optimal filter is what we're really doing. Great. So Monica has a question. She says, I thought they break apart like half and half of the image data. Yeah, so Monica, you're talking, that's a different way to do parallelism. If you look at the paper, it's a great question, Monica. They don't actually break it apart like that, I don't believe. Let's have a look. Yeah, so if you look, Monica, check it out. They don't just split the image in half. You actually don't want to do that. What they do is each of these halves processes the whole image, but there's like 110 total filters, but they break it apart into 2 groups, basically. So each half processes the whole image, but you split apart your filters, basically. So yeah, good question, but it's not broken apart by image. Yeah, so Hernan asks a good question. He says, since the layers are learned, is the pre-processing on the image necessary? Yeah, that's a really good question, right? So do we really have to pre-process by dividing our images by like a mean and standard deviation? Surprisingly, pre-processing still can matter. I know it sounds silly, but pre-processing your image, it doesn't always matter. You can try to leave it out and see what happens, but in general, it's going to do a little better if you standardize your image data. I know that sounds silly. It should just be able to learn, but neural networks are not quite as smart as you might think. They can do some incredible things, but they get it wrong in some really dumb ways sometimes. Neural networks either blow your mind or they're just like idiots. Like it just depends. And yeah, I still recommend normalizing your data, just dividing by like the mean and standard deviation. Okay, so that's the first layer of AlexNet. And what I want to show you next is this. So we have 64 filters. And in the first layer of AlexNet, each of these 64 filters is convolved, right? Really, it's cross-correlation, but it's convolved with the image. And I want to look at the resulting images, because you're going to end up with 64 images, because you have 64 filters. And I want to look at those now. So these are those 64 images. So here they are. So I've just taken the output that I've called a feature map, and I'm just visualizing it. And notice all the different things that happen now. So look carefully here at our processed golf ball. This is after one layer of our neural network. So like, look carefully with me here, right? So if you look at an image like this one, so this one over here, you see those, and maybe I can make this a little bit bigger. You see those, let's do the opposite of what I wanted. You see that the edges are more clearly defined in an image like this. And you see in some of them, different things are more defined, right? So here, you don't really see much of the image, but you see some textures kind of popping out. Here, there's some textures. These are all the different ways that the neural network has learned to look at the image. So, and this one like makes the golf ball texture really, really clear, which is kind of interesting. So it's fun to look through here and see what the neural network has learned to look for after one layer of compute. So that's what happens on the first layer. And there's one thing we haven't talked about yet, well, a few things, but so in this course, we started by using sigmoid activation functions. And again, an activation function is just a nonlinear function we use to let our neural network learn nonlinear patterns. And then we talked about we used tanh a little bit last lecture. What else have we seen? Those are the big ones. So now I'd like to introduce you to a new activation function officially. It's called ReLU. ReLU stands for rectified linear. And ReLU is actually really simple. So this is just an excerpt from the AlexNet paper. This is a ReLU activation function. So it's really boring. It seems way too simple. So for all your inputs less than 0, ReLU is just 0. And for all your inputs that are bigger than 0, excuse me, ReLU is just equal to the identity. So ReLU of 2 is 2, and ReLU of -2 is 0. What is ReLU of 3? Just for fun, throw it in the chat window. What is ReLU of 3? 3, okay, exciting, right? Cool. All right. So I just want to point out one plot from the AlexNet paper. There's lots of good stuff in the AlexNet paper. It's a nice introduction to deep learning. There's some technical jargon and things, but it's worth spending some time on. So here we go. So this top plot, this is training with TAN-H activation functions, just like Jan LeCun did back in the 90s. And the black line, this is training with ReLU. And this is the error, and these are the epochs. So what do you notice? When you train with ReLU, what nice thing happens? Faster, right? Yep, pretty cool. So this shapes the shape of your gradient, you know, so you get downhill faster, basically is the idea. So most modern neural networks use ReLU, or what's called leaky ReLU. It's a very popular activation function. If you're interested in why, there's some explanation from Goodfellow's book. I'm going to keep moving for now, but I would just know that, you know, ReLU is a very common activation function. And what I wanted to show you here, because in our AlexNet neural network, you know, we start with doing a convolution, and then we do a ReLU. The output of the first convolution, I've just picked 4 filters here. The output looks like this, right? And when I do ReLU, I get this. So notice that the output of our convolution has a pretty big range, you know, -10 to 7.5. And what do you notice here, right? You know, you should notice that everything that's less than 0, all these kind of purples and dark greens, all become 0. So it clips the image, right? So it throws away everything less than 0, which might sound arbitrary, but having some type of nonlinearity like this is critical for a network to learn nonlinear patterns. It really won't work without some kind of nonlinearity. And ReLU is one of the best ones that we found. There could be better ones, no one knows, but it's one of the better ones that we have found. Okay, so that's ReLU. And now I want to walk you further. So, you know, we went through this is AlexNet again, the first part of AlexNet. We went through the COM2D, we talked about the ReLU. Now we'll talk about the max pool. And we've talked about max pooling before, so it shouldn't be too surprising. And actually, we'll skip it. So just know that this max pool, you know, it downsamples the image basically. And now we're going to go to the next COM2D. So when I first learned about convolutional neural networks, I got really excited when I saw this. Like, I thought this was the coolest thing. I was like, wow, the neural network has learned these little image patch filters that help find edges and things like that. And I was like, wow, this is great. The next thing I did way back when I was first doing neural networks is I said, okay, I want to make the same visualization for the next layer, right? Like, can't I just visualize the same thing for the next layer? Turns out you can't. So let's talk about why. Why can't you really do the same visualization for the next layer? You can do hacky versions of it, but it's not really the same thing. Let's talk about why. So here's our first conv layer, right? Here it is. And this has a kernel size of 3 by 11 by 11 because our images are 3 pixels deep for RGB, and our kernels are 11 by 11. Here is our second layer. Here it is, right? What is the dimension of our kernel? So throw it in the chat window. What is the dimension of our kernel for the second layer of AlexNet? And I'm going to scratch my foot. Okay, what do you think? What is, yeah, thank you, Abhijit. Excellent. So it's 64 by 5 by 5. Perfect. Okay. Now, why can't I visualize a tensor of that dimension like I did the first layer's tensors? What's the problem? Why can't I just visualize that easily? Yeah, it has 64 color channels. And human color perception is basically 3-dimensional. You may have heard of this animal called the mantis shrimp. There's a really great comic about the mantis shrimp. The mantis shrimp can see in 16 color channels. So if you were a hyperchromate animal like that, and we showed you some images, you could see 16, but you still couldn't see 64. So yeah, humans just can't see that many color channels, so we can't really visualize it in the way that I would like us to, you know, unfortunately. What we can visualize, though, is the output. So these are all the outputs of the neural network after 2 layers. So this is 2 layers of image processing, and we get to outputs like this. And we're going to get into this in more detail in a second with a really cool video. But right now, I think I'd just like to emphasize that notice that some things are starting to get really glowy, right? And some neurons, some activations are starting to get kind of empty, right? That's going to be really important. Here we are after 4 convolutions, after 4. And this is interesting. You start to see higher level patterns, and we'll get into this more shortly, but after 4 convolutional layers, you start to see kind of like, here's kind of a background detector. We're just picking up on the background of the ball. There's some kind of foreground detectors, it looks like. It's starting to learn some higher level structure, we think. So Sai says, so different filters learn different things. How to choose the filter? I mean, the filter values or dimensions. Oh yeah, sure. So yeah, I think Sai, you're asking, I believe, you're asking how do we choose that we should have 192 filters here and 384 here and 256 here? Yeah, so these are the hyperparameters. Just like before, we take an educated guess, but there's no rule about what works. My recommendation is to pick a popular neural network like ResNet, which what we talked about in the Fast AI lecture, and they've done some tuning to kind of guess what's best. But was that your question, Sai? Are you asking about how the parameters actually learn? Because I was just talking about the hyperparameters. If I didn't answer your question, Sai, please give me a little more detail, and we'll talk about it. It sounds like because there's also, we could talk about how the kind of parameters learn as well. I'll keep going for now, though. So this is the output after 4 convolutions here. And what I really, and here's 5 convolutions, and we're starting to see maybe some patterns that emerge. What I think is going to really help clarify this, though, I think there's this really great video. It's actually like 5 years old now or something, but this video is just really cool. This blew my mind the first time I saw it. And I'm going to turn off the audio. I encourage you to watch this. So there's this deep learning visualization toolbox from this research group. I forget which university they're at. I'm sure it says so in the description. But what I really want to show you is this tool, and let's see here. I think I'll play it without audio, and I'll kind of talk through it. So what this tool lets you do is, for a video, you can visualize all the outputs of AlexNet. So here they're referencing the AlexNet paper. So here's a picture of the speaker, right? And what we're looking at are the outputs, right? So like that layer see, he's showing it's a vertical edge detector, right? So he's moving that piece of paper back and forth to show you that, hey, look, this neuron, that's annoying, this neuron is really, really firing on vertical edges. It's really firing on vertical edges right here. So he's kind of showing you that first. And I would recommend watching this. It's really, really cool. So here's the filters that we've already seen. There's those filters. And what they do in this video is they kind of walk up higher and higher. And they also show some really cool visualizations that kind of demonstrate what higher level conv layers have learned. And this is really cool, so check this out. So this is the 5th convolutional layer. And notice that most of the outputs are pretty dim, right? But this one layer has this glowing area, right? So this 5th convolution, which is it's 5 convolutions in a row, but by doing filter, 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 the network has learned a face detector, right? It's found a way to find faces using those 5 layers of convolutions. And as he moves around, right, you see this move around with him. And I think in a second they'll bring a second person into the frame, and you'll see this activation unit will have two regions in it. I think they'll show that in a second. Yep, here we go. And they reference some other papers that kind of talk about visualizing. Here we go, ready? So here comes somebody. There you go. So you got 2 detectors now, right? So this network has learned a face detector. And there's some other ways to visualize what the network is seeing or learning or doing, and that's what they're showing here. I won't cover that in too much detail today just because we don't have a lot of time. But it's a really, really cool video, and they kind of walk, if you're curious, what has this deep learning neural network really learned? This video is great. Okay, so we'll keep moving here. We're going to talk about adaptive pooling a little bit, which we've already talked about in some detail, so we can probably knock that out kind of quickly. We'll talk about dropout a little bit. We'll talk about the linear layers of AlexNet, and then we'll look at the results. And that'll be our AlexNet walkthrough. Okay, so after all those convolutional layers, right? So we walked through all the convolutional layers, the 5 convolutional layers at the beginning of AlexNet. Hopefully that gives you a sense for kind of how they work and what they're doing together. Now the next layer in AlexNet is an adaptive average pooling layer. And it's very similar to a pooling layer, but there's one little difference. Do you guys remember what's the difference between just a regular average pooling layer and an adaptive average pooling layer? What does the adaptive do? What does that mean? Yeah, variable size inputs, that's right. So if the input size changes, an adaptive average pooling layer will always make the output, in this case, 6 by 6. So that lets us have different sized inputs. So that's what adaptive average pooling does. And the very end of AlexNet, this is kind of the head, the end of AlexNet. It consists of 3 linear layers, so 3 fully connected layers like we've seen before in this class. And it also has ReLUs, which we've seen. We just learned about ReLU, activation functions. The one thing we haven't discussed in this class is dropout. And dropout is a really powerful idea. I think it was introduced for the first time, I think, in the AlexNet paper, I believe. So let's have a look at it. So it's actually a pretty simple idea. It sounds kind of dumb. Here's an excerpt from the paper where they explain dropout, and here is an excerpt from the deep learning book where they explain dropout very, very nicely. And I'll just say it in a few words quickly to give you a sense for how it works. So dropout is really, really simple. All we do when we have a dropout layer like this, so you give your dropout layer a probability. So here we have p equals 0.5. So what that means is that it's going to take the output of the previous layer, and for 50% of the neurons, it's going to just zero them out. It's going to basically turn them off. So dropout randomly turns off for every pass. It randomly turns off some percentage of the neurons. If you make this bigger, I always forget which way it is. I can't remember if 1 means all neurons are off or on, but it's in the documentation. But the point is that you're turning off a portion of all your neurons. Now, why would we do this, right? Why would you want to randomly turn off part of your neural network? Why would that ever be a good idea? Any ideas? Why would we do dropout? Yeah, so Abhijit says regularization. Yes, to avoid overfitting, right? So it's a great way to regularize, right? To prevent your neural network from overfitting is to apply dropout. And if you're thinking about, let's say you have a neural network that's overfitting, right? One way to reduce overfitting is to make your neural network simpler, right? So you could reduce the number of layers. You could use less filters, right? You could reduce the number of parameters. It turns out in practice that you can do that. It's a good thing to have. It's a good option to have. But in practice, the first thing you want to try is something like dropout. Because dropout, what it does is by turning off part of your network, it makes your network not do this thing called co-adaptation. It forces it to learn more robust patterns in your data, but you still get the full power of a really deep network with lots of parameters. So dropout kind of lets you have your cake and eat it too. So it lets you have a very powerful deep neural network, but at the same time it helps you reduce overfitting for that big powerful network. So that's the idea of dropout. So yeah, Hernan has asked the perfect question for this moment because I was about to ask the class this, so I will just ask the class Hernan's question instead of me asking it. So Hernan says, does the dropout stay there when not training? So when not training, we normally call inference. So we train a neural network, we freeze it, and then we do inference. We use it to make decisions. So when we're doing inference, what do you guys think? Keep dropout on or turn it off when we do inference? What does the class think? So Jagadish says off. Okay, we've got 1 vote for off. Any other opinions? So Abhijit says they're already dropped during training. So Abhijit, that's a great point. Let me make this a little more clear. So they're dropped during training randomly, and drop just means that the neurons are still there. We just set their values to 0. So if a neuron had a value of 1.6, we just set it to 0. So the neurons are still there, right? So at inference time, we could still do dropout by randomly turning off half of the neurons at that layer, or we could turn dropout off and we could leave all the neurons on for that layer. So we've got an off, an off, and an on, yep. So the answer is off. You want to turn dropout off when you are doing inference. FastAI does this for you. PyTorch will not always do this for you. And let me show you just so you know how to do this in PyTorch. Let's see, do I have an example? I should. Let's see. Okay, it's pretty simple. So all you do is this. So we have our model. So if you want to turn out dropout, usually in PyTorch it's just model.eval is what you do. And this puts the model into evaluation mode. Puts model into evaluation mode. Evaluation mode. That turns off dropout. So Sean, great question. If dropout wasn't random, would you still leave it off? So I've never heard of a non-randomized dropout, because if you just decided to turn off certain neurons, it would effectively be the same thing as just having a smaller neural network without those neurons on ever. So I've never heard of non-random dropout. That's a good question. But we leave it off during inference because it's random and it's going to basically, it's like a source of noise almost, right? So we leave it off. You get better performance in general when dropout is off. So that's why we turn it off at inference time. Yeah, good question. Okay, so that's the idea of dropout. Yeah, so Jagadish says, are we dropping to avoid losing features? Good question. So it has a lot to do with co-adaptation. So I think the AlexNet paper might explain it pretty well. Like here, let's just read a little passage, right? So you guys are asking great questions, right? I want to make sure we spend as much time as we need to on this topic. It's an important topic. So let's read from the AlexNet paper a little bit. I think he's going to explain it better than I can. So let's say the neurons which are dropped out in this way do not contribute to the forward pass and do not participate in back propagation. So every time an input is presented, the neural network learns samples a different architecture, but all these architectures share the same weight. This technique reduces complex co-adaptations of neurons, since a neuron cannot rely on the presence of particular other neurons. I think that sentence for me really helps me understand it. So it reduces co-adaptations. So let's say that you're a little neuron in the 7th layer of the network, and you're trying to learn a face detector, right? You may learn that, in the previous layer, layer 6, where your inputs come from, maybe you always see a strong signal on neuron 75, right? And you could learn to always rely on that same neuron from the previous layer. But with dropout, that neuron's going to be gone some percentage of the time. And if that neuron is gone, then your face detector neuron has to learn to rely on other neurons. So it has to learn more than one way to predict something. It has to learn more than one way to learn. And by doing that, it makes the overall network more robust, because you're forcing each layer to learn patterns that are not as dependent on the previous layer's exact configuration. I hope that's helpful. It's cool, isn't it? Yeah, it's crazy that it works, right? There's a bunch of just tricky ideas in deep learning that are like, man, how did we think of that? So that's the idea of dropout, and really, the AlexNet paper explains it really well, and so does the deep learning book. So if you're interested in learning more, please check out those resources. But hopefully that gives you an idea, and when you hear about dropout in context, you'll know what it means. And if you are training a neural network for this programming challenge or for your project, and you're overfitting, then try some dropout, right? And if dropout's not working, then change the proportion, right? So make it drop out more to overfit less, and make it drop out less if you're underfitting. Okay, I did a little visualization to show you before and after dropout. I think I'm going to keep moving for now, but I'll talk about it just for a second. So I took real PyTorch code. Let's look at size question real quick if it's still about, oh, actually, yeah, so 2 more questions. Yeah, let's chat a little bit. So Abhijit says, are most things just empirically validated or based in theory? Yeah, so Abhijit has asked a great question. He says, all these things like dropout, right? Are these based in theory? Did someone do some math and figure out that dropout is optimal in some sense, in some mathematical sense? Or is it empirical? Did someone just have an idea and try it, right? In deep learning, it's mostly the latter. There's one paper called the Wasserstein GAN paper. You can look it up. It's the WGAN paper. This paper, WGAN, Wasserstein, I'll put it in the chat. This is one of the most theoretical papers in deep learning, one of the most theoretical popular papers, for GANs at least. But most deep learning research is driven today by empirical guesses. You're just trying stuff. when you go write the paper, you make it sound fancy, but mostly researchers are just trying stuff, right? So I hope that's encouraging, because I think it means that if you're doing research in deep learning, there's still plenty of things to discover, and you don't have to be a mathematical wizard to find the next new thing. Most of these things are just empirical. That's a really good question, Abhijit. Sai says, might be a stupid question, but how did they implement AlexNet? There was no PyTorch or TensorFlow. Yeah, Sai, that's a fantastic question. Not stupid at all. So I believe AlexNet was written in custom C++ and CUDA code, I believe. So CUDA is the low-level NVIDIA library for controlling GPUs. And I believe, so actually I'm sure, so Alex Kravinsky had to write this in C++. And well, maybe it was either C or C++ and CUDA. Now, the crazy thing is, did he have an automatic differentiator? I don't know if he did. He might have had to do the calculus himself. It'd be fun to interview him. That'd be kind of cool to learn, right? I don't know, but I know that it was in a lower level language. And I don't know if he had to sit down and do all the back propagation math himself, or if he had some library to do the differentiation for him. But that's a great question, Sai, because you're right. TensorFlow was released in 2015. This was written in 2012, right? So it did not exist. And definitely no PyTorch. Okay, great questions. So I'm going to leave this dropout for further discussion for you guys to review if you'd like to. You may have a question on your quiz about dropout conceptually, but not super detailed. So make sure you feel good about the concept. If you're curious or want to learn more, look at these notes in more detail. Okay, so the last few layers of AlexNet are fully connected layers. And I wanted to visualize those weights, for fun, just so you could see them, because I want to walk you all the way through AlexNet. Here's the 6th layer of AlexNet. It's a fully connected layer. Real quick, just roughly, this layer has 9,216 input neurons, and it has 4,096 output neurons. Throw it in the chat window. Approximately how many weights does this layer have? What do you think? Roughly how many weights? So size says 36 million. Okay. I was just doing the math in the back of my head. I think my number is a little lower. Any other guesses? But I was doing the math in my head, so I could be wrong. Any other guesses about how many weights this layer has? And remember, how do we find the number of weights in a fully connected layer? We talked about this last class a little bit. And actually, I can make this really easy if I just go to images, yeah. So here is an image of a fully connected layer, right? Here it is, right? So if you have a certain number of inputs and a certain number of outputs, I'll make this a little bigger. Right. If you have 3 inputs and 4 outputs, right, the number of weights is just the product. So it's just 3 times 4 in this case, right? So here, it should be 9,000 times 4,000. Which I think is around, I want to say 500,000, because isn't 10,000? No, sorry. No, you're right, Sai. Sorry, I was thinking that this was 1,000 times 1,000, which is 1,000,000, but no, it's yeah, I think I agree. Yeah, so a whole lot, right? So like 36 million, great. Sorry, I doubted your answer. So you multiply these together, yes, math wins, right? Multiplication, right? It's a all right, cool. So it's got a whole bunch of weights, right? Here they are. So these are the 36 million weights in this layer. I've just plotted the matrix as an image. Not a lot of structure here, not much to look at. Maybe there's some patterns you could find by visualizing it other ways, but I just wanted to show them like this. And I think that's our full walkthrough. So, that gets us all the way to that y-hat output, which is that 1,000 dimensional, and yeah, 37 million, yeah, including the biases, I think. So this gets us all the way to that y-hat output, which gives us that golf ball prediction. And I think now we'll kind of wrap up the AlexNet discussion just by talking about the paper a little bit. So here's a figure from the paper. And oh yeah, I want to show you one more thing actually, and this will actually tie in really nicely to our conversation of GANs. So here we go. This is a figure from the AlexNet paper. Again, this is figure 4. And to the left, these are just predictions. So it's saying, hey, you know, here's the image, the network predicted container ship, for example. So that's pretty cool. Now on the right, this just gets really, really, really cool. So, and it's related to GANs. So let's talk about it. So on the right, you have 5. So remember the ILSVRC. That's the name of this challenge, the ImageNet Large Scale Visual Recognition Challenge. So there's test images in the first column. So these are test images. So these are images that were just selected at random, or maybe hand selected from the data set. Now this is where it gets this just blows my mind. So the remaining 6 columns show training images that produce feature vectors in the last hidden layer with the smallest Euclidean distance from the feature vector for the test image. So some of you listening right now to this lecture might have immediately said, oh, I know what that means, got it, no problem. Some folks might think, what the heck what are you saying, right? Let's break it apart a little bit. There's kind of a lot going on here. So let's break this down one part at a time. So it says that it shows images that produce feature vectors in the last hidden layer with the smallest Euclidean distance from the feature vector of the test image. So let's start with what does it mean to say a feature vector in the last hidden layer? What is that, right? So let's get into it just for a second. So here is AlexNet again. Let me get to the whole architecture, which I guess I got to go all the way up here. Sorry, here we go. Here it is. Yep, here's AlexNet. Okay, cool. So the last hidden layer is here, right? Well, actually, it's here. Sorry, this is because this is the output layer. So this is the last hidden layer. So they said the vector, the feature vector output by the last hidden layer. What is the dimension of that vector? How many numbers are in that vector that they're talking about? The feature vector output by the last hidden layer. What is the dimension of that vector? Any guesses? Yeah, perfect. Hernan Abhijit, great. 4096, yes. So it's 4,096 numbers, right? Okay. So for any image, I can take any image in the world, right? I can pass it into AlexNet, right? And what the authors of this paper are saying to do is they're saying, okay, go all the way through, right? But stop right here. Don't do that very last computation, right? Don't do that very last piece of math. Stop right here, okay? Take those 4,096 numbers, and let's use those. We're going to call that a feature vector. Those 4,096 numbers, we're going to call it a feature vector. Let's use those numbers and try to find some structure, some patterns in those numbers, right? In those 4,096 numbers. And before we go back to the paper for a second, I want to give you one more idea. So what you could do is you could take 2 images, right? You could take 2 images. You could do this with both of them. So take one image, pass it through, get vector 1, get the output here, get feature vector 1, and then take a second image and do the same thing. So I have 2 vectors, one from one image, let's say one from image A, one from image B, right? And then maybe I can do some math to compare the feature vectors of those 2 images. Okay, so that's kind of the idea. Now let's go to the paper again. So what they've done here, you take, we'll call this image A, right here, the first image, right? Take this image, compute its feature vector, the 4,096 numbers, right? And then take all of AlexNet, or sorry, all of ImageNet, take the whole data set, right? Pass every single image all the way through to that last layer, compute that image's feature vector, right? And then for all the images in the data set, compare them to the feature vector, compare their feature vectors to the feature vector of this image, and then sample the closest ones. Sample the images that have the closest feature vectors. And that sampling is what you're looking at, right? So this image has a feature vector of 4,096, numbers that are very similar. They're very close in Euclidean. If you measure the Euclidean distance, which is just the L2 norm, if you measure that, these are very, very close. They have very small differences. This should be, I hope this is a little bit mind-blowing, because this is crazy, because we just trained this thing to classify images, right? But it's learned a structure that's incredibly useful, because let's imagine that I said, hey, yeah, and it's an embedding. Yes, that's a great name for it. It's a very popular name for this idea. So Imagine if I said, hey class, your job is to take these 1,000,000 images and figure out which ones are most similar, right? That might sound easy, maybe, but it's actually really, really hard. Because if you think about like, how do you measure image similarity, right? The kind of naive approach is to just take the pixel difference, right? So if I do these pixels minus those pixels, right? Maybe similar images have small pixel differences. It turns out that that works terribly, as you might have guessed, because even though these both show purple flowers, they don't, their pixels are so different because it's a different view, different lighting, right? So somehow this neural network, just by learning to classify images, has learned, it's called an embedding space. It's learned an embedding space that is semantically meaningful. And it means that in that embedding space, the distance between vectors corresponds to the similarities between images. So you can use that embedding space to find patterns like this, which is, it's crazy. And GANs take that a step further, basically. I hope that makes sense. There's a lot to unpack in the AlexNet paper. We could talk about the AlexNet paper for like 6 lectures. It's a really great paper. So that's the idea of an embedding. I hope that makes sense. If it doesn't, please review here. This is something I probably would quiz you on. It's a really important concept. Okay, so there's one last piece of magic maybe to talk about. Maybe there's 2 things. Yeah, okay, just a few more things, and we'll go on to generative adversarial networks. We have about 25 minutes. I want to talk about transfer learning, because when AlexNet came out in 2012, no one thought you could do transfer learning as well as it turns out you can. So real quick, we talked about transfer learning very briefly in the Fast AI lecture. What is transfer learning? Throw it in the chat window. What is your definition of transfer learning? Yeah, so reusing a trained model, right? So you train a model on one task, and you transfer that model to a new task, and you use it to try to solve that task. You might train the model further, but it's the same model that you started with on task A. So that's transfer learning. This is a great figure from a paper by, and sometimes you will remove the last layer. Yes, sometimes in transfer, often you will. So this is a paper by Razanvian, I think, and Donahue. Yeah, okay, 2 papers. But this figure is from one of these papers, and this is just like, this is crazy. So what they did is they took a bunch of tasks. So they took a bunch of different computer vision tasks. Here's like 10 different tasks. And for the green bar, they're showing like the very best state of the art in that task before deep learning. So this is like an accuracy score, I think. So like 100 would be the best. And the green bar is the very best, approach to that problem before using an approach like AlexNet. Excuse me. And the red bar, this is taking a model like AlexNet, right? And it's fine tuning it, it's specializing it to this task, right? Actually, I think that's the blue bar, excuse me. The red is just doing this plus a little augmentation. But the thing that's crazy, and like the green bar, this was like years and years of research in computer vision, right, to get to this level using hand design features, all kinds of stuff. For all of these tasks, kind of like out of the box, if you take AlexNet and have AlexNet try to solve this task with transfer learning, it does better than the very best research in the world on that project before. So AlexNet just like changed everything, because all of a sudden, just using transfer learning and a pre-trained AlexNet model, you could outperform the very best state of the art in that problem before. So I hope that makes sense. This was like a revelation. So the fact that you can do this is not obvious, and it really makes deep learning very, very flexible. So that's transfer learning in a nutshell. We've discussed data augmentation, but I just want to make sure that you're aware of it. Data augmentation is the idea of making synthetic changes to your data set at training time usually. So at training time, you might flip your images, you might adjust the color. Here's some examples, right? So here's the original image, and here's some augmented versions of that image. So here I've kind of changed the brightness, here I've changed the colors and flipped it, here we've kind of scaled it and zoomed it. Why do this? Why would it make sense to augment or modify your images when you train? Any ideas? Why would this be a good idea? Yeah, so it makes you appear to have more data. What kind of problem might augmentation fix? If you're training a neural network, right, and something as bad is happening. Yeah, again, it's all about overfitting. Life is about, machine learning is about overfitting, yes. So it reduces overfitting and it helps your neural network generalize. Data augmentation is a huge deal. In my day job, I probably spend more time on data augmentation than I do actually training. So data augmentation is really, really important. Okay, so be aware of that. It's built into FastAI. PyTorch has some nice libraries for it. I think I walk through how to do some data augmentation in PyTorch here. So if you're interested, you can grab it there, or you can get it from FastAI. So that's there. There's just one last thing I want to say about deep learning, and we're going to go on to GANs, which are also deep learning, but a different way to do them. Okay, so there's just one last point I want to make, and this, the history here really, I think, is fascinating because it hopefully helps us think about the future. So I already asked you this question, but I want to ask you again, or at least talk about it again. So, why didn't deep learning take off in the 2000s? So, most of the technology was there in the 90s. Why did it take another 10 or 20 years to become a thing, right? Why didn't we figure this out sooner? So here's a comparison in detail between the two neural networks that we've studied here. So if you recall, we looked at AlexNet, the AlexNet neural network. Here it is. Cut off and everything. And here is the LayNet 5 from 1998. So these networks are 14 years apart, right? But one of them kind of launched this huge explosion of deep learning, and one no one really cared about. So, I mean, they did a little bit, but this was not a really popular paper at the time. So what's the difference? Let's look. So the training set was different, and this arguably is a big part of the difference. So the LayNet 5 model was trained on MNIST, 60,000 examples, 10 classes. AlexNet, it's a much bigger data set. It's 1 order of magnitude bigger. It's 2 orders of magnitude more classes, so a much more sophisticated data set. As far as compute, this is a big deal, right? So LayNet 5 was trained on a Pentium 2 with 0.27 gigaflops of compute. 14 years later, Alex Kravinsky had at his disposal, what is that? That's like 10,000 times the compute power. So he had, with the two NVIDIA GTX 580s, he had, 10,000 times the compute power. So that matters. Data plus compute make a big difference. As far as the architecture, it's not dramatically different. So LayNet 5 had 5 layers. AlexNet had 8 layers. Now we use networks with 50 layers pretty comfortably. Different activation functions. So actually, this should say TAN-H, I believe. TAN-H sometimes. ReLU activations in AlexNet. AlexNet had dropout, which is a new innovation. So how many, what does FLOP stand for, actually, before I just blow through all this? What does FLOP stand for? One of the challenges of lecturing online is that when I'm in person, I can look at the class, and if you guys have like your eyes glazed over, then I know I'm going too fast. So Ashish says CPU cycle, yeah, close. I mean, yeah, that's part of it for sure. It corresponds to a cycle, sure. Or it can, depending on your architecture. But what does the acronym stand for? FLOP, F-L-O-P. What does that stand for? And what's a G-flop and what's a M-flop? Any ideas? Thank you, Abhijit. Yeah, so floating point operations. Floating point operations. If you put an S on it, it stands for floating point operations per second, just like Sean said. Awesome. So what I wanted to point out is how much compute is required for these networks. So a forward pass, when you pass an image through the network, it takes 0.8 megaflops, 0.8 million floating point operations. And AlexNet takes 0.7 gigaflops. So you have about 3 orders of magnitude, so it's just bigger. And then as far as tooling, right? So Alex Kravinsky didn't have TensorFlow, he didn't have PyTorch, but he did have CUDA, right? Which makes a difference for sure. So this is kind of what changed, but what's really interesting is like all of the ideas were there, right? Really to unlock this, it was a matter of more compute and a matter of more data. But you really could have done this stuff earlier. It's not, there were supercomputers that could have gone this fast. It's really interesting. There's a couple quotes about it in case you're interested. So I'll just share one quote with you really quickly. The quote is this, it's from the Goodfellow's book. At this point in 2006, deep neural networks were generally believed to be very difficult to train. This is 2006. We now know that algorithms have existed since the 1980s. They actually worked quite well. but this was not apparent in 2006. The issue perhaps is simply that these algorithms were too computationally costly to allow much experimentation. So it was difficult to experiment with. But there were no actually like science barriers. Does that make sense? So in the early 2000s, there was no reason you couldn't do this. It was really just there wasn't enough, really, I mean, no one did it, right? No one had the time or the experimental ability to try this out until 2012. But all of there was no, in 2012, there was no like one magic idea that made it work, right? Which I think is just fascinating. Okay, great. So Monica says big tech companies also had a big role in deep learning popularity. Yeah, I agree, Monica, but not before 2012, though. Really, 2012, no tech companies were even doing it, really, until this paper came out. But now they definitely have been a big part of popularizing it. So, Google and Facebook and all these guys use deep learning for all kinds of stuff. So yeah, GPUs advanced so fast now it's teraflops. Yes, and I think an iPhone 12. How many teraflops? iPhone 12 teraflops. Um, yeah, so an iPhone 12 has 2.6 teraflops. So that's pretty crazy, right? So the network used to train AlexNet had, the hardware used had 3,000 gigaflops. So the phone that will fit in your pocket, an iPhone 12, has, what is that, like 6 or 8 times more compute power, which is really crazy. Okay, so that is all I'm going to say about deep learning in depth. I hope this gives you a good overview of the important topics in deep learning. Some things have changed since 2012. I'm kind of giving you the state of the art in 2012. To really use all those modern advancements, I recommend you use the Fast AI library. It implements all these modern advancements like ResNet really nicely. But this really, if you pay attention and follow these lectures and read these notes, this should give you a sense for the important things in deep learning, in my opinion, even today in 2020. So that's deep learning. And now we will transition to a really fun topic. It's our very last topic for our deep learning module. And like I said, we may finish this one up after Thanksgiving. We'll see how much time we have, but we have a new module to start then. We'll see, but we'll spend a little bit of time talking about GANs. I just want to get you thinking about this thing called a GAN. And this is not something that I'm going to quiz you on. It's a little bit, this is kind of the cutting edge of deep learning today. But I do want to show you, it's really, really cool stuff. So let's go back to 2014. So this is 2 years after the AlexNet paper came out. So this guy, Ian Goodfellow, he wrote the deep learning book that we're referencing here. Super smart, he's very creative too to come up with such an interesting idea. So he published this paper in 2014, and he said basically this. He said, okay, if you can solve this equation, if you can write an algorithm to solve this equation, we'll talk about this equation shortly, but he gave this equation. He said, if you can solve this, you can make fake data that is completely indistinguishable from real data. And he proved it. He proved mathematically under a set of assumptions, if you solve this equation, which we'll talk about what all these variables mean, but he showed mathematically, if you solve this equation, you can make fake data that will be indistinguishable from real data. And data could be audio, images, whatever, right? So it has some theory in it, but it also has some practice in this paper. So that's the idea of the paper. These are some figures from the paper. So let's look at them here. So this is the MNIST data set. The yellow is real, I believe. Let's make sure. Visualization of samples from the model. The rightmost column shows the nearest training example. Yep. So these 5 images are all fake, and this one is real. So what he's trying to show you with the real image is that it hasn't just memorized. So these are fake handwritten digits created using Ian Goodfellow's algorithm, which became called GANs. I think he did call it a GAN at the time. Here are some faces that were made. Yeah, so Sai, we'll get to that in a second. Yes, here are some faces that were made, right? Here are some kind of animals. Well, it doesn't look great. This is from a data set called the CFAR10 data set. So, he basically in the paper, he said, hey, if you solve this equation, you can make completely realistic images. It turns out you can't really fully solve this equation. We'll get into it in a little bit, or these notes will at least get into it. But these pictures look okay, right? But they're not that, like, if someone showed you this picture, you could tell this was not a person, right? It's not that convincing. They're okay, but they're not amazing. But what's really interesting is what happened next. So if we go forward 5 years, let's go forward 5 years to 2019. So using very similar technology, progress has been made, a lot of progress, onto generative adversarial networks. And let me ask the class now. So here are 3 images of people. Which one do you think is fake? We'll call this 1 over here on the left. We'll call it 2, and we'll call it 3, right? All right, which one do you think is fake? So Hernan says the middle, Supri says all. What do you think? Ravina says the middle, Marty says all. Any other guesses? The middle is kind of the most popular answers are the middle one and the all 3, right? Okay. For those of you who said all 3, maybe you know my trick. So yeah, these are all fake. None of these are real people. This is from a paper called Style GAN, which I should have a link to. Do I not have a link to Style GAN? I guess I don't. So I encourage you to go look at Style GAN. It's crazy. So it uses the same idea that Ian Goodfellow thought of. Let's find the paper real quick. Oops. Style GAN 2 is out now too, which is even, oh my God, I can't click on, okay, there we go. I guess this actually came out in 2018. Okay, so yeah, here's the original Style GAN paper using the same idea that we're talking about. I don't know why it's taking so long to load, but let's look. I just want to really look at one of these images together. It's crazy. Yeah, here we go. This is a really nice figure. This is where I took those from. So here's a bunch of not real faces. Maybe you've seen this research before, but I mean, if you look at these details, like holy crap. Like, I mean, if you look at the hair, you can kind of tell, like just barely. The hair is going to have a little noise to it. But this is, this is not a real person. This person has never been born, does not exist, not a person. This is the most advanced technology in the world for making synthetic images, or synthetic images of faces, excuse me. This one has more noise, but the level of detail is just, I mean, it's just crazy, right? That we can synthesize images like this. Okay, so that's why we're talking about GANs, because they've come so far in 5 years. And it turns out using GANs, you can also do all kinds of really kind of science fiction things. You can fill in missing parts of images. You can transform low-res images into high-res images. This problem is called super resolution. You can make captions from images. You can generate images from captions, which I know sounds crazy. You can compose music, you can synthesize audio, you can synthetically age faces, you can make fake videos of people dancing, you can generate training data for other models, you can predict depth maps from images, you can find anomalies in images, you can do a bunch of stuff. Now, GANs are still research, right? I haven't seen a lot of GANs in like production systems here and there, but GANs can do impressively well at all these tasks, but they aren't perfect, is what I would like to say. But it's still an area of a lot of excitement, and it's an area that's worth spending a little bit of time on. Yeah, so Dinesh says, how do we differentiate a noise and low quality image? Great question. So really, we'll get into exactly that question when we talk about GANs. Fake art, or what about art fake currency? That's funny. Yeah, maybe, right? Okay, so you can do a bunch of stuff with GANs, but what I really want to just spend a little bit of time talking about is how do they work, right? How does a GAN actually work? Because now that you know some things about neural networks, you're really set up to understand GANs really well. Because a GAN is just an extension of a neural network. It's not different at all. It's really just 2 neural networks put together that train a certain loss function. So here's my figure of a GAN, and I have 6 whole minutes to explain a very complicated idea, so I'll do my best. Bear with me. But if you're curious, I encourage you to look at the notes, and I've given some good resources on GANs too. But I'll try, in a nutshell, I'll try to explain GANs in 5 minutes. We'll see how we do. Okay, so here's my figure of how GANs work. So this is Ian Goodfellow's big gross equation. Here it is. And here is my figure to help you think about how these things learn, how they learn to make fake data. So in a GAN, we have 2 neural networks. So not just one, we have 2. We have one neural network that's called a discriminator, and it is very similar, basically the same as the classification neural networks we've been seeing, just like AlexNet. But AlexNet has 1,000 classes that it predicts, and a discriminator only has 2. It only has 2 classes. So the 2 classes that a discriminator predicts, it predicts true or fake, right? So it predicts whether or not an image is real or not real. That's what the discriminator predicts. That's its job, to tell apart fake and real images. A generator has the opposite goal. So a generator is a little bit of a different kind of neural network. It goes from smaller vectors to bigger images using what's called a transpose convolution, which we'll discuss if we have time. But just know that it's a neural network, and its input is a vector. Let's say that this vector is like 100 units long. It's a vector of length 100, for example. And its output is a fake image. And as we'll see if we have time, when you initialize a generator, it just outputs noise. It's just like, random noise images. But as the whole system learns, the generator becomes better and better at faking, which we'll see why in a minute. So there's two neural networks. You got your generator and your discriminator. And so how do you train it, right? What do you do? So what you do is you take random noise. So this sounds weird, but you take a random vector of length 100, right? You pass it into your generator, right? And you make a batch of fake images, or you can do it one at a time if you want. You make a fake image. And you take that fake image and you use this to train a discriminator to tell apart real images from fake images. And it might sound like, okay, how does a generator get any better, right? It might become clear that we could train a discriminator like this, right? And kind of the magic of Goodfellow's idea here, it's really, really interesting. So let me explain it in a little more detail. And we'll get into the training loop if we have time, but you do a training loop, and basically every other loop, and I see a lot of comments. I'm excited to check these out. I'll do it at 3:45, but especially related to GANs. I'll finish explaining kind of the basics here, and then at 3:45 we'll kind of end, and then I can look at some of these comments. Right, what I want to get at is this. So how do you train this thing? So hopefully it makes sense that if you have a fake image and real images, you can train a neural network to try to tell them apart. I hope that makes sense, because you kind of get your labels for free because you know that these are real because you just grabbed them from a set of real images, and you know that these are fake because they came from a generator. But how do you train your generator, right? How does this thing get smarter, right? The way it gets smarter, it's really, really cool. So you take your discriminator, right? And you can actually do back propagation. You can do back propagation all the way from this loss function, all the way from here, back to these weights. So the back propagation flows through the fake image. That might sound crazy, but you basically, for every training step, you take a step for the discriminator, you train it, you take an iteration and improve the discriminator, and then you improve the generator. So you train the generator to be better at fooling the discriminator, which that's what this math really says. So you optimize the generator's weights to try to fool the discriminator while you simultaneously train the discriminator to better classify the generator images. I hope that makes sense. If not, don't worry about it too much, but that's the core idea. The core idea is that these two networks take turns learning, and they learn to optimize different things. That's the idea. So yeah, Abhijit asks a great question. Why do we need a vector of random noise and not just one random number? So it really has to do with the embedding space, Abhijit. So it's a great question. So if we just had one random number, right, the neural network would kind of predict the same picture every time. I hope that makes sense. If you use dropout, it might be a little bit random, but it's really going to predict the same image every time, and the discriminator can quickly learn that that one image is fake, right? But if you use a different set of random noise every time, then it's going to make different looking fake images, so it keeps the discriminator guessing, basically, right? That's one reason. There's other reasons to do it too, but I think to me that's the one that makes the most sense. It's to make these fake images look different every iteration. So your discriminator has a harder job. It can't just memorize that this one fake image is fake. So that's the idea. The last thing I just want to say is that there's two big differences. So the one difference between a neural network and a GAN is that you have two neural networks that are trained at the same time. The other difference is the loss function. So this really describes the loss function for a GAN, but it's not really a loss function anymore. It's really what's called a value function. And the reason is that you don't want to just minimize one thing. You actually, if you think about the parts of your network, they actually have different goals. So the discriminator, it wants to get the result correct. If the image is real, it wants to predict a 1, and if the image is fake, it wants to predict a 0, basically. The generator has the opposite goal. it wants to, if the image is fake, it wants the discriminator to predict 1. It wants it to do it wants it to be wrong, right? So all you really do, there's a lot of nuance to it, but you just flip it, right? So you have this value function, and at the same time as you train, your generator is trying to minimize the value function, and your discriminator is trying to maximize the value function. So really, if you look at the theory behind this, it's really like playing a game. So the math that goes into this, a lot of it comes from game theory. So you have these two networks kind of fight. They play this game together. And if it goes well, they achieve what's called a Nash equilibria, named for John Forbes Nash, who is a game theory mathematician in the 20th century. And if they achieve this Nash equilibrium, that's the condition where you have perfectly fake data, which it's impossible in practice, but that's how the theory works. So that's the idea of a GAN. We're out of time for today. We have a guest lecture next week and then Thanksgiving, so we won't talk about GANs for a while. We may talk about them a little bit when we come back from the break, but if you're curious, please go through these notes. You know, there's other resources to look at too, but hopefully I've given you a little bit of a taste for what a GAN is. And GANs really have to do with the idea of embedding. Here's an animation of a one-dimensional GAN training. You can have a look at if you'd like to. And then we go through training a GAN on the MNIST data set. So that's really GANs. I hope that gives you just a little flavor for how they work. We can go ahead and end the recording for today. And I saw a few comments, so I'll look at those real quick, and we'll close that for today. But I hope that all makes sense. We covered some more deep learning, and we really dug into some of the early details about GANs. And if you're curious, go look at the notes. And I think at the end of the notes, we end up training, yeah, here is an MNIST GAN that generates fake handwritten digits. I think it's about to be done training. Okay, cool. So let's go ahead and stop the recording. Thank you guys for coming today. We'll see you on Tuesday for should be a really good guest lecture. Make sure you come on Tuesday. I'm looking forward to Andrew Edelman. He has a huge amount of experience deploying deep learning. So we're talking about theory and stuff here. If you're interested in getting deep learning into the real world, Andrew Edelman, it's going to be, I'm excited. So make sure you come on Tuesday, and let's go ahead and stop the recording, please.